Hi there, this is Dr. John Whitcomb talking about how our genes work, and that's Understanding Longevity Part 1. This is going to be a 4-part series, and I'm really reviewing David Sinclair's work done in Lifespan. I want to explain it in a nugget. Here's the key idea. We really have the genetic code to live to be 120, okay? But we stop reproducing at about age 40. And thereafter, nature isn't much interested in you if you aren't reproducing. And so many things start to fall apart. Well, let's look at our genetic code and say, what's falling apart? Why are we falling apart? And here's the insight. You have about 10% of your genes on your DNA. If I look at your chromosome, if I scrape a cell off your forehead and stretch out the chromosome, the DNA in it, you have about 20 feet of DNA. And only 10% of it are the 22,000 proteins that make you a unique individual. The other 90% is your operating system. And in that coding, those genes are packed into a very tiny little cell. And they're all wrapped up with proteins called histone proteins. Now, as you get older, your genetic code does not degrade. Your genetic code is immutable. Okay? But your epigenome, which are the labels, the hundreds of thousands on each chromosome of labels on the surface that identify when to hold them, when to fold them, when to activate a gene, when to put it to sleep. That epigenome is all defined by methyl groups and acetyl groups that are on and turning you on and off. You don't need to know that detail. But what you do need to know is that that's what degrades and gets us older. The health of your epigenome is the key to how long you live. Okay, and that's what starts getting older at age 40. And you can measure it. You can actually there are now companies that will tell you your age of your epigenome. And you can see how functionally old you are. Are you as old as your calendar says, or are you younger because you're following a healthy lifestyle? All right, so the very first cell that came along had to have DNA to duplicate itself with, but it also had to have the gene to repair its DNA and to repair itself. And those are your sirtuin proteins. You have 7 of them. They are tasked with the job of housekeeping your epigenome. Now we can do elegant experiments in mice that can show when you can't repair your epigenome, you age faster. And that's what's happening in humans. That's what's happening in you and me. Our epigenome degrades and can't be repaired because our sirtuin proteins don't work. And part of why our sirtuins age is they run out of energy. So very probably the very first cell that came into being had NAD, which we call niacin, or vitamin B3, as the first energy supply. And as we get older, our NAD runs out. So our sirtuins can't fix you. So you run out of the management of your epigenome. That's why we get old. So next week I'm going to talk about the Horvath clock, and we're going to have 3 more and explain how to keep your epigenome healthy. Do pay attention. This is a fascinating story. Or read David Sinclair's book, Lifespan.